So this is in fact enzyme kinetics, so we have to add the enzyme at some point. And so we're going to put up a reaction coordinate that should look somewhat familiar that you've seen before. So delta G as a function of reaction progress here. We're going to think about free enzyme and free substrate that are existing separate from each other, but they can then bind to produce the enzyme substrate complex. And then a reaction occurs, right? So we got a big hill there because it's a chemical transition state. We're actually breaking and making covalent bonds. Once that reaction occurs, then we produce the enzyme product complex, and then the enzyme and product can part ways, unbind from each other, and produce free enzyme and free product. And so that should look familiar from the catalysis lecture. But now that we have an understanding for kinetics, I want to convert that reaction progress diagram, that free energy diagram, into what we call a reaction scheme. And so we're really just following the progress of this reaction. So we start off with free enzyme and free substrate, and it's in equilibrium. That can react, or rather bind, via a rate constant called K1 to form the enzyme substrate complex. Well, the enzyme substrate complex could just fall apart and reform free enzyme and free substrate, and that we're going to call K-1. Alternatively, the enzyme substrate complex could react to form the enzyme product complex. We kind of call that K2. But enzymes are catalysts. They reduce the energy of activation. They don't irreversibly do anything. The reaction can go in reverse. And so we have so potentially the enzyme product complex could reform the enzyme substrate complex. We're going to call that K-2. And then finally, the enzyme product complex can fall apart. The product can unbind, and we can have free enzyme and free product again. We're going to call that one, guess what, K3. And then the enzyme and product binding to form the enzyme product complex, we're going to call K-3. Notice that the way this kind of follows the scheme, we've got the substrates, products, any of these intermediate complexes are the flat wells of this, and that the arrows, K, represent essentially going through transition states, as we would expect. There's going to be certain height, certain activation energy for these processes. Now, what we're concerned with in enzyme kinetics is the rate of change of product over time, right? Remember back to those rate laws. What's the rate of product formation over time? And if we look at this right here, if we are watching a reaction and we want to measure product formation, well, that's kind of difficult because product is being formed from the enzyme, but also that product could rebind the enzyme and the reaction can go in reverse. So that's kind of a mess. And so we have to do something special in order to really just look at one part of that. We really just want to look at one of those arrows. And so what we're going to do is simplify everything via the initial velocity simplification. And this is where we're going to measure the reaction rate early. That's the key thing with the initial velocity simplification, is that we're going to do everything early during the course of the reaction. Now, this plot, instead of delta G, we're going to have concentration as a function of time. And we're going to, if we think about time zero, what I'm going to do, we're going to have the enzyme ready. We're going to give it its substrate. There's going to be no product around. Substrate up here at, now the units of concentration, we're not really looking at concentration, we're looking at proportion, but you get it. So 100% of everything around is substrate, and 0% is product at that point, right? As we would expect, we're going to decrease the concentration of substrate, and it's going to achieve some equilibrium position. I'm not specifying exactly where that's going to be. It could be close to zero. It might not be zero. It depends on the specific reaction. But of course, if substrate is being reacted into product, then the product concentration is going to go up. And that might look like that. Again, I'm not specifying exactly what percentages those go. Well, what's important about this is if we look sort of, and I tried to draw this somewhat carefully, notice that if we're looking kind of in this time frame early on, that the lines depicting the concentration change are rather linear. Substrate concentration is far greater than product concentration early on. And that's actually really important because I'm going to go back one to kind of look at this. Think about this scheme. What happens if there's no product around? If there's no product around, then K minus 3, we don't have this reverse arrow. In other words, there's no product around for the enzyme to bind. So the only way that we form the enzyme product complex is via K2, where the enzyme is actually catalyzing that reaction. Now, if there's not a whole lot of product around, then if any EP is made, right, any product is made in the active site, chances are it's going to unbind. It's way more likely to unbind the enzyme because this hill is small and there's not much of product around here. Way more likely that this will unbind than it'll go backwards. So essentially, if we do a reaction where there's no product at the starting point and we measure the change in product concentration early, we eliminate K minus 2 and K minus 3. Now what does that look like? So we now have E plus S makes the enzyme substrate complex via K1 minus K1, produces, but now there's no K minus 2, so there's only a forward K2 to produce the enzyme product complex and a forward K3 to produce the free enzyme and free product. Okay, well, we can actually simplify that even further because if we make enzyme product complex via K2, the only thing it can possibly do is unbind. And so really we don't need to have both K2 and K3 separate. We can combine this whole thing into one arrow. Okay, so let's redraw that. So now we've got enzyme plus substrate, form the enzyme substrate complex. We got K1, K minus 1. And then we go straight to free enzyme and free product. And now we're going to call this thing, because it's really all about the catalytic step. It's all about what's going on in K2 producing the product. We're going to call it KCat. This right here is going to be the basis of so much of what we do with enzyme kinetics. It's called the initial velocity scheme. As long as we are measuring the reaction at early time points during the course of the reaction, it'll greatly simplify our analysis of enzyme kinetics.